Hi, I'm Jeff. This is a training course about NumPy. It is part of DataBeans Data Science training course, and this is the first unit. We are going to learn ndarrays. What are ndarrays? Ndarrays stand for n-dimensional arrays. It is NumPy's main object. It is fast and space efficient. Remember in the previous unit, we talked about the performance of NumPy. Vectorized computing in NumPy can be as 177 times faster than the native Python list operations. ndarray data structure is part of the reason. In Python list, you can put different types of objects into it. But in ndarrays, all elements must be of the same type. Let's take a look into an example. Here we create an ndarray. I use the question mark expression to bring up an interactive help from Jupyter. You can read through the document if you like. Just need to get a sense of those attributes. And let's find out what they are. Ndim is the number of the dimensions of the array. 2 means a two-dimensional array. Shape is the shape of the array. In NumPy, dimensions are called axes. Sometimes we use XYZ to call the axes, for example in matplotlib, and sometimes we use columns and rows, for example in pandas. But in NumPy, we can have as many dimensions as we like. So we call it the first axis and the second axis, and so on and so forth. When reading the values of the shape attribute, like here, we will say the first axis has a length of 2 and the second axis has a length of 3. D-type stands for data type. We know Python has many data types. NumPy doesn't use the native data type, even though some of the data type looks similar. Instead, NumPy uses a special object containing information used to precisely describe the data. For example, there are 4 types of flows in NumPy, including flow 16, flow 32, flow 64, and flow 128. In our example, D-type is flow 64. Size is the number of elements in the array. We need to distinguish the value of size and the value of len operator in Python when applied to ndarray. We'll talk about it later. Then item size, which is the size of memory use of each array element in bytes. One flow 64 object uses up 8 bytes of memory. Data is the buffer containing the actual elements of array. We don't usually look into this attribute, but good to know how ndarray map to physical memory. Now we have some idea of how ndarray look like. Let's see how to create those arrays. Let's look at one-dimensional array first. The easier way to create an array is to use the array function. This accepts any sequence-like object and produce a new NumPy array containing the past data. We can then check the value of ndim and verify the result. When check the value of shape, we can see only the length of the first axis, which is 4 here. There are 4 elements in the array, which make the value of size 4. And since this is the one-dimensional array, the value of size is exactly the same as the value of the len operator. Creating a two-dimensional array is similar, and we actually did it before in the first example. It is not necessary to write the code as what I do here, but I found it easy to read if I put it this way. Then we check the value of ndim and the value of shape. Nothing unexpected though. But when we look at the result of len operator and compare it with the size attribute, we can see the value of len operator is actually the same value of the length of the first axis, which we can tell from the value of the shape. Now let's look into the 3-dimensional arrays. A 3-dimensional array is an array of 2-dimensional arrays. Isn't that obvious? Yes, but I'd like to point it out because not everyone can understand the concept of it when first look at a three-dimensional array, especially when we get confused with the three-dimensional space. If you still have a hard time to understand what a three-dimensional array is, look closer to how I lay out the code and read the array layer by layer. Now let's check the value of shape and endime. Although we can understand the array layer by layer from inside out, but NumPy names the order of access in the opposite way. The length of the first access is 2, and the second one is 2, and the third one is 1. Not surprisingly, the result of the length operator is 2, which is the first element of the shape. And the item size is 8, indicating each element occupies 8 bytes in memory. There are functions that can help us create ND arrays. Let's begin with the three simple but important functions: zeros, ones, and empty. As the name suggests, zeros help create an ND array with all elements set to zeros. We give the function the shape of the target array, such as 3, 4 in our example. Then check the value of endime and shape. We can see dtype is float64, which is the default data type of using zeros function. Using ones is similar. It helps create an ND array with all elements set to 1, 2, 3, 4, meaning the length of the first access is 2, the second is 3, and the third is 4. But what if we want to create an ND array of elements of int16? We can do that by assigning the parameter dtype to NumPy int16. Finally, let's take a look at function empty. We also give it a shape. Then we call it multiple times. We can see the values of the elements in the arrays are not always the same. This is because empty doesn't initialize the memory. The ones, zero, and empty function all come along with the like functions, which help create arrays like an existing one in shape and data type, but set the values of the elements to ones, zeros, or not initialized. Here we can use a previously created array, A, and make some new arrays using the like functions. Notice how the empty like function works. To create sequence of numbers, NumPy provides a function analogous to range in Python that returns arrays instead of lists. We used this function in a previous unit for performance testing. It is as simple as providing the number of elements in the sequence we want to create. Let's check the function's documentation. Notice the dtype is none by default, which means the return data type will be determined dynamically. Here come some more complex examples. We give 3 parameters, and the corresponding arguments are 10 for start, 30 for stop, and 5 for step, which means creating an array starts from 10 instead of 0 and stop before 30 with each step as 5. That's why we get 10, 15, 20, and 25. But we can also use float arguments. In this example, we start the sequence from 0 and end before 2, with step as 0.3. In this case, we get 0, 0.3, 0.6, 0.9, 1.2, 1.5, and 1.8. We use NumPy array above to create arrays from sequence-like data. I'd like to bring another similar function to your attention. It is NumPy as array. Here we create 2 arrays using these 2 functions respectively, and they look exactly the same. What's the difference? The difference is in the details. Using NumPy array, by default, it will create a new array using data passed to it. While using NumPy as array, it will try to convert the data into NumPy array. This difference looks subtle but very important for data processing. When creating a sequence of numbers that's splitting evenly, we can assign a step to create a sequence, like what we've done previously using NumPy arrange. But there is another useful function. NumPy linspace can do the similar thing but in a different approach. Instead of assigning the step, linspace takes an argument of the number of samples to generate it in the sequence and calculate the interval by itself. We also need to keep in mind linspace by default includes the stop value, while a range function doesn't. A typical usage of linspace is to evenly divide the x-axis between 0 to 2 pi's into a designated number of data points, for example 100. We don't want to manually calculate the steps before we can call NumPy arrange in this case, although NumPy arrange is very useful in other scenarios. Today we learn about ndarrays and how to create them. Hope you find this video helpful. If you want to learn NumPy or other data science related topics with me, please subscribe to my channel. There are more to come. Thank you for watching. Until next time.